All right, guys, good morning. Good morning. We're kind of wrapping up the last hypothesis test on chi-square goodness of fit testing this week before our quiz tomorrow and final next week. So if you look at the calendar here, quiz 11, last quiz for standard 23. I'm sorry, standard 22 is tomorrow over chi-square goodness of fit hypothesis testing. And then we have the course DMAC final scheduled for next Thursday, a week from tomorrow, May 14th. Are there any questions I can talk about or answer, clear up any concerns you have before we move on? I did send out a study guide for tomorrow's quiz earlier this week. I'd be happy to go over any questions you have either now or at the end of the call. Okay, if not, let me pull up my slides for today. We're looking at goodness of fit testing using a chi-square distribution. A goodness of fit test is statistical inference on whether or not the distribution of a categorical variable fits an expected model or an expected distribution. How good of a fit is our data to some theoretical model? This formula here is our chi-square test statistic. It's also found on your formula sheet in the bottom right corner under the chi-square column. That kind of slanted X is the Greek letter chi. It's not chai. Chai is a latte. It's a drink. This is the Greek letter chi. Chi square is equal to the summation, that's sigma or summation, of the observed data minus the expected data squared divided by expected. This formula keeps track of the difference between what we're seeing in our observed data and what we expected to have seen for some theoretical distribution or model. Now we need to square it because sometimes we're going to be above the expected value, sometimes we'll be below the expected value. Differences don't matter if we're above or below, so we're going to keep track of those differences by squaring them and then add them all together. The conditions for a chi-square goodness of fit test are outlined here. I need to have a random sample of data where each expected count in the categorical variable categories is to be more than 5. A little bit of background on the chi-square distribution down here. It's right skewed because I would expect that my data fits some distribution. There'd be very little difference between what I observe and what I expect for the model. So chi-square values are typically very small, very close to 0. It would be much rarer for us to get a chi-square data point, chi-square test statistic that's greater than 10. Now they're based off of the degrees of freedom for the different categories in our model, where I have n-1 degrees of freedom. And you can see the different distributions graphed for the different degrees of freedom. The higher the distribution, the higher the number of degrees of freedom, the more normal my distribution becomes. Also, because we're squaring, chi-square is non-negative. It's always 0 or more, 0 or higher. Okay, so I've got a couple of questions here that I just snipped and copied into our slides for this morning. Question 1. After getting trounced by your little brother in a children's game, you suspect that the die he gave to you to roll may be unfair. To check the die, you roll it 60 times, recording the number of times that each face 1 through 6 appears. Do the results cast doubt on the die's fairness? So we have what each face shows. You rolled a 1, 2, 3, 4, 5, or 6, and we rolled this many times for each value. I got 11 1s, 7 2s, 9 3s, and so on. So this is my observed data. This is what I actually rolled. Question A says, if the die was truly fair, how many times would you expect to see each face? Well, we roll 60 times. How many different times would I have expected to have seen each number rolled? my expected, well, 60 divided by 6 means that each one of these should be 10. I would get 10 ones, 10 twos, 10 threes, 10 fours, 10 fives, 10 sixes. Now, obviously, that doesn't happen here. Is it because the die is unfair and I wasn't supposed to get an even number of values? Or is it just normal variability? That's what a goodness of fit test will answer. So part A, we kind of ran through that. If the die is fair, how many times would you expect each face to show? 10 apiece. 60 dies, 1 through 6, 10 of each value. Letter B, to see if these results are unusual, will you test goodness of fit, homogeneity, or independence? We're talking about goodness of fit because we're going to see if our data models some theoretical distribution. So I'll go GOF for goodness of fit. Now for letter C, state your hypotheses. We have a null and alternative hypothesis. So let's assume for our null hypothesis that the die is fair. Which means in our case, we get 10 of each number. We're expected to get 10 of each number. For the alternative hypothesis, the die is unfair. In other words, we're not going to get 10 each. Questions so far? Okay. Now it says to check the conditions. The conditions are outlined here. Rolling a die is a random sample. I need to have at least 5 ones, twos, threes, fours, fives, and sixes. Expected, well, I expect to roll 10 apiece, so that's not a problem. Check the conditions. Conditions are satisfied. We have a random sample, and I expect at least 5 of each number to have been rolled. Letter E. How many degrees of freedom are there? Well, we have 6 categories that make up the distribution of the variable. So 6 minus 1 is 5. That might be helpful in talking about setting up the critical value. Here's our chi-square model with 5 degrees of freedom. It's always right skewed, so we're going to put the significance level, the chance we reject a type 1 error, in the right tail. So for 5 degrees of freedom, what is that critical chi-square score? Let's go to our chi-square sheet. This is on the back of your T table. It says table chi right there. So for 5 degrees of freedom at the 5% significance level in the right tail, you can see here, we've got a similar distribution drawn down below on the left. My critical value is 11.07. So if we can calculate based off of our data, a chi-square score that is more extreme, greater than 11.07, we have significant results. All right. Letter E asks us to do some math. Find the chi-square value and the p-value. The chi-squared formula is the summation of the difference of observed minus expected squared divided by expected. So what we're going to do is we're going to take 11 minus 10 squared divided by 10. 7 minus 10 squared divided by 10, and so on. All right, so for rolling a 1, we got 11, we expected 10. So 11 minus 10 is 1. 1 squared is 1, divided by 10. This is chi-squared. For the 2's, we had 7 2's, we expected 10. 7 minus 10 is negative 3. We square it to make 9. 9 divided by 10. For the 3's, we rolled 9 3's, we expected 10. 9 minus 10 is negative 1. Negative 1 squared is positive 1, divided by 10. For the 4's, we got 15 4's. 15 minus 10 is 5. 5 squared is 25, divided by 10. Notice that the more you are away from what you expect, the larger this value is. So the greater the difference from what we would typically see as a norm, the more we're going to increase our chi-square value. When I don't differ very much by what I would have expected, I don't increase my chi-square by very much. Let's see here, the 5's. 12 5's, we're supposed to have seen 10. 12 minus 10 is 2. 2 squared is 4, divided by 10. Then lastly, 6. 6 minus 10 is negative 4. Square it to make 16. 16 divided by 10. Since these all have a common denominator, we can add them all up. 16 plus 4 is 20. Plus 25 makes 45. This would be 55, 56, 56 tenths. Or 5.6. Compare this test statistic back to our critical value. Is 5.6 more extreme than 11.07? Certainly not. So we are going to fail to reject the null hypothesis. We lack evidence that the die is unfair. Any difference from what we should be rolling, like the fact that I got like 15 different 4's, is just normal variability. We also need to find the p-value, and that is done using Google Sheets. Just like we have t-dist to help us find the p-value for a t-score, we'll have chi-dist for a chi-square p-value. All right, so into some cell, we're going to type equals chi-dist. It needs our test statistic and the number of degrees of freedom, so 5.6, comma 5. And my p-value is going to be 0.3471. P-value means if the null hypothesis is true, what's the chance of our sample or sample more extreme? If the die is truly fair, we would find 60 roles with data like ours about 35% of the time, which does not fall in our 5% range for error. So we have to fail to reject. What else did we have to do here? Oh, state your conclusion. We did that. We lack evidence to say that the die is unfair. Any questions there? Okay. I had one more. I'm going to give you guys about 5 minutes to either work through this on your own, or if you want to work more questions off the review guide that I emailed earlier, that's certainly fine too. Let's take about 4 or 5 minutes. I'll give you a head start, and we'll kind of go over it together as a class. If you have a question while you're working and want to pipe up, feel free. I'd be happy to work through some of these with you while everyone else is working on their own. I'll leave my screen up so you can see the question. Go ahead and get started. About another minute, guys. No problem. All right, let's see what we got. Master Foods Company says that until very recently, yellow candies made up 20% of its milk chocolate M&Ms, red another 20, orange, blue, and green 10 apiece. The rest are brown. On the way home from work, an individual brought a bag of plain M&Ms. They got 29 yellow. So let's just do observed. We had yellow, red, orange, blue, green, and brown. We had observed and expected. So for this person, they got 29 yellow, 23 red, 12 orange, 14 blue, 8 green, and 20 brown. So that's a total of how many M&Ms? 29 plus 23 plus 12 plus 14 plus 8 and 20 makes 106 M&Ms in the bag. They expected that red were 20%. So 106 times 20% is 21.2. I should have gotten 21.2 red. Orange, blue, and green were 10%. So 106 times 10% is 10.6. Orange, blue, and green. We're all 10.6. Yellow was also 20%, so that should be 21.2. I did not quite get that written down. The rest are brown. So it's 20, 40%, 7%, 30% should be brown. 106 times 30% is 31.8. How many of each color for part A? That would be this column right here. Letter B, if the bag is unusual, should they test goodness of fit, homogeneity, or independence? We're going to test goodness of fit. How well does our bag of M&Ms fit some given distribution? For C, write the null and alternative hypothesis. So let's assume that the bag fits the model, fits the distribution. Bag does not fit the model. Check the conditions. We have a random sample of M&Ms. That's not too hard. Let's hope it's picked a random bag. Each expected count here is more than 5, so we're good to go. See, how many degrees of freedom? There are 1, 2, 3, 4, 5, 6 different colors of M&Ms. 6 minus 1 is 5. So if I draw the distribution again, I want to reject a type 1. I want to reject a true null hypothesis, make a type 1 error only 5% of the time. I believe that was the same critical value 11.07 from our previous number 1. So if our test statistic is more extreme, greater than 11.07, we have significant results. And there are, in our bag, a different distribution than the one we're given. Okay, let's see. I think we have F and G. Find the chi-square and p-value and state your conclusion. All right, so observed minus expected. We had 29 minus 21.2 to square. That's 62.41. Divided by 21.2. Plus for red, 23 minus 21.2 is 1.8. Square it, it's 3.24. Divided by 21.2 again. See, orange, 12 minus 10.6 is 1.4. Square it, that's 1.96. Divided by 10.6. For blue, 14 minus 10.6 is 3.4. Square it, it's 11.56. Divided by 10.6. Green, 8 minus 10.6 is negative 2.6. Square it, that's 6.76. Divided by 10.6. We add one more down here. For the brown, 20 minus 31.8 is negative 11.8. Square it, that's 139.24. Divided by 31.8. All right, so chi-square equals, grab my calculator. All right, I got 9.389. For our p-value, we have a test statistic of 9.389. with 5 degrees of freedom. 0.0945. Which does not fall within our range of 5% to reject a true null hypothesis. So we have to, for our conclusion, fail to reject. We lack evidence to show the bag of M&Ms does not fit the given distribution. Because the chance, let's see here, our p-value, if the chance, if the bag actually did fit the given distribution, the chance that we find a bag such as ours is 9.45%, which is not within the 5% alpha type 1 error probability range, so we have to fail to reject. Working through that on your own. Were there any questions that I could answer for anybody? Were there any other questions off the review, other practice problems, life questions in general?
Should we always just assume that it's a 5% rejection region?
Yeah, just kind of that's a statistical norm for any hypothesis test at all. 5% unless told otherwise. It's kind of that Goldilocks, not too big, not too small. It's not 1%, it's not 10%. It's 5% in the middle.
Okay.
Anything else? Okay, we will see you guys tomorrow. Same time, same place for the quiz. Have a lovely afternoon.